same throughout, or it looks uniform throughout, but it's actually broken down to the molecular level. All right, so you've got two parts of the solution, a solute and a solvent. What's the difference in those? What's the difference between those? Solvent is what the solute goes inside of. So how do you decide which is which if you have a solution? So water is a solvent, and all right. So what if you talked about an alcohol solution, right? Which probably a lot of us could use right now in various ways. But some alcohol, you can take a little bit of alcohol and dissolve it in water. But what if you took a little bit of water and dissolve it in alcohol? Does that change, or is water still a solvent? Right. So I think the definitions of these are actually much more basic. The solute is the thing that there is less of, and the solvent is the thing that there is more of.
Couldn't it be vice versa though? No.
Well, no, because that's the definition. So if there's less of it, it's the solute. If there's more of it, it's the solvent. So in our example,
okay.
If you've got a solution of
Water and alcohol.
Water and alcohol, like let's say wine, and the alcohol is like 10% or something in the wine, then you'd say alcohol is the solute because there's more water.
Got it.
But if you had something like grain alcohol, Everclear or something like that, which is a high alcohol. No, it's 95%, so it's like 100 and whatever that is.
Wait, what is it?
Grain alcohol, like pure,
Yeah.
the purest alcohol you can buy without
It's
special
banned
licensing.
in America, isn't it?
No.
You can only get it like.
Maybe not in Illinois, but you can certainly get it in other states.
What's that green stuff?
Anyway, so grain alcohol is way more ethanol, way more alcohol than water. So in that case, water is the solute and alcohol is the solvent.
Okay, so what does it mean when it's like, I was reading like a wine bottle that said like it was 11% alcohol. What does that mean?
Yeah, we're gonna get into that today.
Meaning there's only 11% alcohol.
The rest is apple juice.
Well, it's actually it's a little bit more complicated than that. So hang on to that. We'll get to it in a couple minutes because we are going to talk about those different measures of concentration. All right, so if the solute has less of it, the solvent has more. That means that we can have all kinds of different solutions besides what we think about as solutions. Like when I say solution, you have something in your head, like maybe the blue solution of copper dissolved in water or something like that, or salt water, or sugar water, or alcohol. But there's actually many more varieties. So here's a table from your book that shows some examples of solutions that you might not have thought about. So you can have a gas solution, gas dissolved in another gas. Air can be considered a solution of oxygen and some other stuff in nitrogen, because most of air is nitrogen gas, and all the other stuff there's less of. So nitrogen gas is like the solvent, and all the other stuff is like solutes. And then you've got various liquid solutions. You can dissolve gas in a liquid. You can dissolve liquid in a liquid, like the alcohol solution we just talked about. Solid in a liquid, like what we've, probably the more classic solution that you're thinking of. Let's go back to gas in a liquid. So some examples they give: soda water, carbon dioxide dissolved in water. Ammonia is ammonia, which is a gas by itself dissolved in water. Hydrochloric acid is another good example of that. HCl, hydrogen chloride, is a gas when it's pure. You dissolve hydrogen chloride in water and you get hydrochloric acid. So the acid part is actually a solution in water. And then you've also got something you probably really don't think about as a solution, but solid solutions. A solid dissolved in another solid. And things like metal alloys, like steel. There's no element steel. Steel is mostly iron, and then it has other stuff in it, like carbon and chromium and other types of elements, depending on what you want your steel to do, nickel. And so those things are all dissolved in the iron matrix. Brass is also a solution of zinc and copper. Those are also known as alloys. When metals are combined together like that. But they're really a type of solution. All right. We looked on Monday about how different kinds of solvents react with different kinds of solutes. If you remember, we compared water as a solvent with cyclohexane as a solvent, and then we tried to dissolve some different things in them. And we came to some conclusions that some things work better in one solvent rather than the other. And so one way that that's kind of shorthanded, and certainly is in our lab, is to say, well, you've got a polar solvent to dissolve polar things and a nonpolar solvent to dissolve nonpolar things. But I think we need to think about that a little bit more carefully, because that's not exactly right. Let's look a little bit about how this polarity affects solutions. So if we look at water, let's draw a water solution. This is what a water solution would look like. We'd have water molecules, remember, that have a dipole or a polar bond. So you have a partial negative charge on the oxygen, partial positive on the hydrogen. And these are all connected together in a big matrix throughout the whole solution, throughout the whole solvent. So that's pure water. That's what it's going to look like. A bunch of water molecules connected together, positive parts lining up with negative parts to associate it with each other. And what do we call those types of forces? Hydrogen bonds, right. So that's called hydrogen bonds, which we know is a confusing term because it's not a covalent bond. It's just an association of plus and minus, but we call it a hydrogen bond. And we know it's a pretty strong force in terms of how those intermolecular forces go. It's a type of a stronger dipole force. So when an ion, like, let's say we add some sodium chloride to water, what happens, well, first we can look at what sodium chloride is. So sodium chloride is sodium ions and chloride ions all packed together, right? All alternating throughout a whole solid. So what we have to do to get these things to dissolve is we need to break up those hydrogen bonds in the water. We need to break up the sodium and chloride ionic forces, and then we need to put them back together with the sodium and chloride in between the water. So that's going to look something like this. So now, instead of that hydrogen being attracted to the negative oxygen, that chlorine ion is going to sit in there, and water molecules, because remember, water is the solvent, so there's more water, with the hydrogens pointing at that chloride. And the rest of the molecule can still form its network as usual, but the hydrogens will kind of surround the chlorine, the negatively charged chlorine. And then the oxygens will surround the positively charged sodium. And you can look up what that actually looks like, the number of atoms that actually go around each ion and so forth. But the ions become then sequestered from each other in these what we call solvation spheres of water molecules that surround the ions and keep them from each other. So in order for a solution to form, the solute, the intermolecular forces of the solute, or the things that hold the solute together, have to be similar to the things holding the solvent together. So if you try to dissolve something nonpolar, like iodine, I2, that would be a molecule like that. Now, that doesn't have polar forces. That's not polar because there's no difference in electronegativity, right? Also something that will be on the exam on Monday. There's no difference in electronegativity between the two iodine atoms. So we don't expect any polarity or any negative or positive bits there, which means that in the solid form, this is kind of stacked up with other iodine molecules, happily enjoying their forces. And what are those types of forces called? Anybody remember? The nonpolar forces? Well, the bond is covalent, but what are these forces that kind of hold them together? Hold the different molecules together? All right. Those are, yeah. Those are called dispersion forces. That's the weakest one. So it's still a force, and it's still strong enough to hold these things together and, you know, make a solid compound, but it's not strong enough, or it's not as strong as hydrogen bonds. So when we introduce iodine with water, the iodine molecules don't break up from each other in between here because they don't have any reason to. They're not going to be stabilized by water molecules being around them because they're not polar. So the nonpolar molecules would rather stay with themselves, and the polar molecules would rather stay with themselves, and so you don't form a solution when these things mix. That means that to dissolve iodine, you need something that can do these same kinds of forces. Water can't do that, but ethanol or alcohol can. And so when you see an iodine solution, it's often in ethanol. So like, I don't know if you ever used iodine solution, like for disinfecting something, if you're going to have surgery or something and they have to wipe you off with that brown stuff, that's an iodine solution. What? Insert in what? Oh, yeah. So that's a, yeah. Right. So that has iodine dissolved in ethanol, not water. So the ethanol can actually surround it, or sometimes isopropanol, which is rubbing alcohol. It has the same thing. All right, so that's really how the polarity works. So I'd like you to think of it in terms of how the forces interact with each other, rather than just polar things go with polar things and nonpolar things go with nonpolar things. That's usually how it works out. But an example of how that doesn't work out actually is that iodine. So iodine is nonpolar, and it's in ethanol, which is actually a polar solvent, right? Because we know ethanol mixes with water just fine, like in our alcohol example. I know many of you are too young to have tasted alcohol, but some of you are not, right? So anyway, but ethanol is actually a polar substance. And so if we just say polar things with polar things and nonpolar things with nonpolar things, it doesn't make any sense. Why would ethanol dissolve a nonpolar thing like iodine? So a better way to think about it is, if it can do these forces, then it can do this. So ethanol looks like this. It has 2 carbons with hydrogen surrounding them. And then it has an O and an H. So the OH part is very polar, just like water. But this other carbon-hydrogen part is nonpolar, just like cyclohexane or something like that. So that means that sometimes ethanol can dissolve some nonpolar things, sometimes it can dissolve some polar things. Sometimes ethanol can't dissolve some ions because it's not polar enough for some types of ions. So we have to be a little bit more careful than just saying polar goes with polar, nonpolar goes with nonpolar. A better way to say it is the polar types of interactions, like hydrogen bonding, dipole forces, water type forces, interact with similar types of forces. So plus minus type attractions still hold. The nonpolar forces interact with nonpolar type solvents. And so sometimes those can be in the same molecule, sometimes not. But that's a better sense of what's going on. Okay, so one thing we talked a little bit about before, but we're going to formalize it here, is what happens when you dissolve something like sodium chloride in water. The ions break apart. So remember back, I think it was a couple labs ago, we talked about, or we did a demonstration with the light bulb, and we tried different solutions, and some of them the light bulb turned on and some of them it didn't, or it turned really faintly. And that had to do with, do you remember the word that we used to describe that? Electrolyte, yeah. Yeah, electrolyte. A strong electrolyte is a molecule that dissociates. What does dissociate mean? Right, break apart. So it completely separates from each other. An example of that, a good one is sodium chloride. So you take a sodium chloride solid, you put it in water, and you have exclusively sodium ions and chloride ions sequestered by water molecules, as we drew earlier. So that's kind of a quick approximation, but the idea is the sodium and the chloride ions are completely separated from each other and surrounded by water. And so a strong electrolyte, the reason it's called an electrolyte because it conducts electricity well. Electricity. That's where that word electrolyte comes from. These are solutions that can easily pass an electric current. And how we saw that was that allowed the current to flow through the light bulb when we put that solution under there and make a really bright light. So it allows a path for the electricity to flow because it can jump from ion to ion. A weak electrolyte dissociates slightly. So it breaks apart a little bit. A few molecules break apart, but most of them don't. The example we saw in lab was acetic acid. Another example of that is HF, hydrofluoric acid. So you put that in water, and you get some hydrogen ions and some fluoride ions, but you also get a bunch of HF that's still just HF, and that hasn't broken up. And this one conducts electricity not well. We'll just say conducts electricity meh. Yeah, it's a poor conductor. Just kind of not so great. And then, so that's going to lead to a dim light bulb. And then we have a non-electrolyte. Which does not dissociate. So this is a molecule that when you put in water, it dissolves like sugar. Here, table sugar is C12H22O11, right? Yeah. So you take solid sugar and you put it in water, you make sugar solution. Right? It dissolves. You put sugar in water, it goes in there, but it doesn't break apart. None of the atoms come off. It doesn't form any ions. So no ions formed, no dissociation, not an electrolyte. Won't pass electric current. And we saw that a couple weeks ago. The sugar solution did not make the light turn on. So electrolytes you may hear in a medical context. What are they important for in the body? Why do we care about electrolytes in the body? I mean, I'm not a biologist, so.
It brings back certain minerals and vitamins that your body's lacking.
Right, but what do those do? Why do we refer to them as electrolytes instead of just, minerals or vitamins? Yeah, it's actually because they this idea of conducting electricity is really important in the body. A lot of how nerves work depends on electrical signals that get passed by moving these ions. So positive ions move from here to here, which creates a current, and that causes this nerve to do this or this thing to do this. So you actually need these electrolytes in your body to pass these appropriate signals. So why do you need them sometimes? How do you lose electrolytes? When you sweat, so a lot of those ions come out through your sweat. You throw up or have a lot of diarrhea or something like that, you can lose electrolytes that way. And then there's also the opposite, where if you drink too much water, you can dilute them out and not have enough electrolytes. So those are all issues that, and so common electrolytes in blood are sodium, potassium, magnesium, calcium. Those are the positively charged ones. And then the negatively charged ones are chloride, bicarbonate, hydrogen phosphate, and some proteins, actually, some negatively charged proteins. So that's what electrolyte means. It has to do with the electrical conductivity, but really it deals with how it forms ions in solution. Okay. So let's see, what should we do next? Let's talk now about, because this is kind of a little quick, and then we'll get into concentration. Solubility. What does solubility mean? What is that? Right, so the ability to form a solution. That ability is the key on the end of the word there. It's how well does it form a solution? Does it have the ability to form a solution? And so how is it measured? So we did a little bit about solubility on Monday, and we're going to go into these calculations in a little bit. But there's what we would call a qualitative measure of solubility, meaning that we just sort of shake something up and we look at it and say, oh, it's soluble, or oh, it isn't soluble. But that's not really good enough. We want to be a little more precise than that, a little more quantitative than that. We want some numbers. So we want to measure exactly how much of this solute we can put into the solvent before it stops dissolving. So anybody notice the sodium chloride solution on Monday, the thing that you were boiling off in a little dish? There was a bunch of solid on the bottom of the bottle. Anybody notice that? So what does that tell you about that solution? There was too much solid in there, right? There was more solid in the bottle than could dissolve in the solution. That's actually was on purpose. So what do we call that when a solution has all of the solute, or a solvent has all the solute that it can possibly take? We know what the word for that is? Well, you've gotten to the solubility point, that's correct. There's a name for that type of solution. Close. Saturated, yeah. So a saturated solution, in a saturated solution, no more solute can dissolve.
Unsaturated.
So unsaturated means there's less than that. Unsaturated means more solute can dissolve. So you can run these tests and you can figure this out. You can figure out what the saturated concentration is. You can keep adding, let's say, sodium chloride to water, keep mixing it in there, and then at some point that water is not going to get to clear up when you shake it anymore. The sodium chloride is just going to fall to the bottom and not dissolve in the water. And that's when we have a saturated solution. What's happening on the molecular level, do you think, at that point? If we go back to our model of a solution here, where the water is surrounding these ions to dissolve it, what causes it to go the other way? What causes when it's saturated, why can't more just go in? What's happening there?
According to this explanation of
Mhm.
the sodium chloride, the amount of oxygen and hydrogen molecules surrounding the sodium or the chloride, they are lesser than sodium and the chloride itself, so they are kind
Right.
of diluted.
Yeah, that's right. So at some point, you don't have it. You can say that you don't have enough water molecules to really surround these things properly and hold them in solution. And so the additional ions don't have water molecules to surround them anymore, so they can't go into solution. So they stay in the solid. So that happens at that saturation point. Now this changes with a substance, and it also changes with temperature. So I'll show you this graph. Okay. Here's a graph from your book of solubility versus temperature. So it means how many grams of a solute can you dissolve per 100 grams of water. Any more than that, they're going to start falling out of the solution and just sticking to the bottom. So I know this is kind of a busy graph. Let's focus first just on this NaCl line, this yellow line right here. So this says that at room temperature, so 22 degrees or so, you can dissolve about 38 grams of sodium chloride in 100 grams of water. If you try to dissolve 50, some of it's going to get left on the bottom. See that? As we increase the temperature, that line goes up a little bit. So by the time we get to boiling water, we can dissolve just about 40 grams, so not much more. But you can see some of these solutes change drastically. So glucose, a type of sugar, at room temperature, it looks like about here you can dissolve just over 80 grams of water, or of glucose in 100 grams of water. You go up just another 10 degrees, and suddenly you can get 112 or so. Right? As you go up, you get more and more. The potassium nitrate that we used on Monday is in this orange curve here. So you can see as the temperature goes up, the solubility changes dramatically. And this is what you were testing on Monday and what we're going to calculate in a little while. So if you had, let's say, 100 grams of potassium nitrate per 100 grams of water, so that would be like 1 gram per 1 milliliter, or how many milliliters of water did you put in there? Do you remember? Was it 10? 5? 10? Okay, so for 10 milliliters, that means you'd have 10 grams. So if you had 10 grams of potassium nitrate, you heat it up, and most of it doesn't dissolve, most of it doesn't dissolve. When you get to this point, it's going to all dissolve. So out here, it all dissolves. You cool it back down, and when you get to about 55 degrees, suddenly it's going to start coming out of solution again, and you saw that happen. And so that temperature, where it starts coming out of solution, is the temperature at which that much is no longer soluble. So this is true. It's not true that every solute increases solubility with temperature, but it is true that most of them do. The big exception to that, in terms of water solution, is gases. So for gases, increased temperature decreases solubility. And this is known as Henry's law. A couple examples of this. One, if you've ever had a carbonated beverage, like a pop or a soda, you had that. Okay, you got it right there. Everyone was sort of just staring at me blankly, so I don't know if this was a foreign concept or something. So if you open 2 cans of pop, you put one in the fridge, you leave one out on the counter, which one's gonna go flat faster? Yeah, the one sitting out on the counter. What? Okay. It's probably good. It's not really good for you. But so the one sitting out will go flatter faster because the CO2 is not as soluble in the warm liquid. So you cool that liquid down, and now it's going to hold that CO2 for longer. It's another reason why we take ice in our drinks, right? Sometimes, sometimes just because you like really cold drinks, but it also helps them stay carbonated for longer if you're planning on sipping it over a period of time. A more pressing and probably important example is in the oceans. So there's lots of gas dissolved in the ocean. There's lots of CO2 dissolved in the ocean. There's lots of oxygen dissolved in the ocean. And as ocean temperatures warm, I'm thinking here because of climate change, those gases get released. They're no longer dissoluble. So we've already got a problem with too much CO2 in the atmosphere causing the warming of the oceans. As those oceans warm, they will themselves start releasing more and more CO2 in the atmosphere, kind of making things worse. And that's what's known as a feedback loop, where one thing happens and then it causes even more of the effect because of something else. And that's also because of this idea. What? Actually, that says whatever can go wrong will. That's not really a true thing, but yeah, it's it's like a saying, right? So this is so if you think about those examples, then you can remember that it's actually opposite from what we're more used to seeing. So I guess we should go back. What are some examples that you've seen of how temperature affects solid solutes? Most people come up with things like cooking here. Ideas? Anybody cook? No? Just drink soda?
What did you ask?
When do we dissolve a solid solute and we use an increase in temperature to help that dissolve better?
Oh, melting water. I've tried to dissolve sugar in very cold water.
Right.
It takes a little bit of time.
Yeah.
Dissolve that in just lukewarm water.
Right. Right. So that's a good example. It's much harder to dissolve sugar in cold water than in hot water. Which I don't know if anybody ever notices, if you go to McDonald's or a place like that and you get an iced coffee or some kind of a thing, they don't use actually solid sugar for that. They use a syrup because the solid sugar wouldn't dissolve very well. So they use a liquid sugar instead, or sugar syrup. And sometimes we'll do that for different types of drinks too. In hot coffee, it's not a big deal because the sugar dissolves right away. In cold coffee, it doesn't. And we can see that on this glucose curve. That's sucrose, but similar behavior. As you heat it up, you increase that solubility. If you ever made something like rock candy, you can dissolve sugar in water, and you can heat the water and get as much sugar as you can, and then you slowly cool it. And as you cool it, those sugar crystals grow out of the solution, just like the potassium nitrate crystals grew as we cooled down that solution on Monday.
No, that's like, I just wanted to ask as well, like dissolving bicarbonate in water, what happens? Like, I know it builds up the gases, so does it happen with the temperature?
Yeah, so one thing that you'll find is if you put, there's a couple things there. Part of it is this, you're right, and another thing is the reactions that are happening. Like if you're baking with baking soda or baking powder, and then when you put something in the oven, it's going to give off that carbon dioxide gas, which makes the cookies get, fluffy or cake or whatever. Yeah. Yeah. So that's partially this, but it's also the heat is speeding up the reaction, speeding up the chemical reaction, actually making the bubbles form more. Yeah. So it's really bold. Okay. So now we've talked about all these kind of general properties of solutions. So the last thing to do is to look at some specific measures of how much solute is in the solvent. And this goes back to your question from before. What do these numbers mean when we see these different we see these different types of concentrations. So this word is called concentration. And the concentration just tells us how much solute per unit of solvent or solution, depending on the measure. So how much salt do we have in our water? Or how much salt do we have in our salt water? Now, because different things are used for different things, and sometimes it's easier to do it one way or do it another way, we have several different measures of concentrations. So we're going to go through them and kind of look at each one, how we calculate it, how we use it. Some of them are more popular in everyday use, and some of them are more popular in like lab type use. They all come up in medicine because medicine never can decide on units. So you'll get, an IV bag that has all kinds of different concentrations of different kinds of ions and proteins and sugars and whatever else. So you have to have a good facility with them, just like with other units, so you don't get confused about what's actually there. All right, so we'll start with the percent concentrations, because that's kind of the most, what we're most used to. So the first one we can look at is called mass percent. And sometimes that's written as M over M, or percent by mass. The reason it's written that way is because the equation for mass percent is the mass of the solute divided by the mass of the solvent times 100%. Oh, I'm sorry, not mass of the solvent, mass of, that doesn't make sense. Solution. Okay. So if we had, let's say, 30 grams of sodium chloride and 120 grams of water. The sodium chloride is the solute, water is the solvent. So the percent by mass, or the percent M over M, would be the mass of our solute, which is 30 grams, divided by the mass of the solution, which is the total mass. So we've got 30 and 120 together is 150. And we should make a special note of that because that's a common mistake. So this is going to be both of them added together. 30 grams sodium chloride and 120 grams of water. Right, it's everything together. So the mass of the entire solution. Okay. And so 30 from the adding the two parts of the solution up, the total mass of the solution. So we should specify that. The bottom, the denominator, is the total mass of the solution, not the mass of the solvent, the total mass of the solution. So 30 divided by 150 is 0.2, multiplied by 100%, that makes a 20% by mass solution. All right, so this would be called a 20% mass over mass sodium chloride solution. Percent by mass is a commonly used measure for sure. It's used when volume doesn't make sense. So certainly for things like solid, if we're looking at steel or other kinds of alloys, those are always going to be given in mass percents or percent by mass concentration. Also with solvents, if the solute and the solvent are both kind of, we could say important, like it matters how really exactly how much of each there is, then mass percent is good because you know exactly the mass of the solute, you know exactly the mass of the solvent because you know the total mass. So if you need to know exactly both, mass percent is the way to go. The drawback of it is it's not always as convenient because if it's a regular kind of a common solution of something in a liquid, liquids are more easily measured by volume usually than mass. So we'll prefer some kind of percent that deals with volume rather than mass a lot of the time. And then so there's two varieties of that. The first one is volume percent, or V over V, or percent by volume. And as you might expect, this is very similar to the mass one, just with volume instead. So volume percent is volume of solute divided by the volume of solution. Yes, the total volume of the solution. Yeah. The reason I didn't put total is because volumes aren't additive, meaning that if you have 10 milliliters of this thing and 10 milliliters of this thing, and you mix them together, you don't necessarily have 20 milliliters because they intermix in different ways, and so you don't always get that. Like if you mix alcohol and water, if you mix 10 milliliters and 10 milliliters of water, you don't get 20 milliliters total. You get like 18-ish because of the way that they mix with each other. They don't break down, but they kind of go in between each other and change the overall volume. So you can't just add up the volumes to get the total volume. You need to actually measure the total volume. So volume percent is not something we use a lot in the lab because of that, because with volume percent, you don't really know exactly how much of each thing you have. But it's often a convenient measurement in other ways. Like, so this goes back to your question about the alcohol before. When you look at a bottle of alcohol, wine or something, it'll report the alcohol content by volume. So ABV, alcohol by volume, which is a percent, a volume percent calculation. So that's the percent by volume of alcohol based on the overall volume of the solution. And so we can calculate that in the same way, but we need the total volume of the solution. So if we did an example, the example of the book, what? Is what? The total, right. Yeah, so like a 750 milliliter bottle of wine, we know we have exactly 750 milliliters. So let's do an example. So let's say you have a 750 milliliter bottle of wine. Wine is something that you drink for the younger people here. It has alcohol in it. What?
No, it's.
Depends on the wine. Depends on the wine. All right, so let's say that this wine has a 12% ABV on the label. It says 12% ABV. So that's 12% alcohol by volume, or in our new way of writing things, we would say that that's 12% V to V, 12% volume. 12% by volume. All right, so we can calculate now how much actual alcohol or ethanol is in there. Because we've got our volume of solute, which we don't know, and our volume of solution, which we do know. So we'll set up the equation with the same way. Volume of alcohol divided by 750 milliliters times 100% equals 12%. So something divided by 750 equals 0.12. Right, so 750 times 0.12 is, I don't know, I'll calculate it out. So that's 90 milliliters of alcohol. So if you could distill that wine, which people do and make other kinds of alcohols, if you could distill all the other stuff off or separate the alcohol from everything else in there, you would get exactly 90 milliliters.
Why didn't you times the 750 by 100% though? And then divide that by 12%?
Well, so I first divided the 12 by 100 to make 0.12.
Oh, okay. And then you multiply.
Yeah. The book uses the example of lemon extract solution. So extract solutions like vanilla extract, lemon extract, all those kinds of things are solutions in alcohol usually of some flavor molecules. So so they're kind of diluted down a particular percentage, and you can see the percentage of that on there as well. Okay. So we won't use volume percent too much, but it's good to know what it is because that comes up outside of this a lot. One that we do use is called mass volume percent. It's kind of a hybrid of the first two. So mass volume percent, or M over V. As you can imagine, this is going to be a certain amount of mass of solute in a certain amount of volume of solution. That's really useful for most of the standard solutions we make because we're usually dealing with a solid and then making a liquid solution out of it. So mass volume percent is going to be grams of solute divided by mils of solution times 100%. Now notice I specified the units here. In the other percents, the units need to be the same on the top and the bottom, but it doesn't matter what units you use. So mass percent could be grams to grams, kilograms, kilograms, pounds, pounds, whatever. Volume percent could be liters, liters, milliliters to milliliters, gallons to gallons, doesn't matter. But in mass volume, you have to have the same, you have to have the proper units or your numbers are going to be all over the place. So it's got to be grams of solute divided by milliliters of solution. Or, so it's got to be grams per milliliter wait, it's not grams per milliliter, that's density. It's got to be grams divided by milliliters or kilograms divided by liters because that's 1,000 on both sides. But we'll almost always stick with this just because we are usually dealing with smaller scales of things. So let's look at what that looks like because that's what we've done in lab as well. So what you do when you make the proper way to make a solution in a lab, which we haven't really done yet, is you use something called a volumetric flask. Volumetric flask has a fat bottom and a skinny neck, and it just has one line on it that goes around. So it doesn't have all the different, things like a graduated cylinder. It just has one line, and it has some indication of how much it is. So what these things are meant to do is measure one volume very precisely. Just one. So a 50 milliliter volumetric flask can only measure 50 milliliters. But it can do it really, really precisely. It can go to 50.00 usually, 50.00 milliliters, sometimes more. So what you do is you put your solid, you put a little bit of liquid in, you dump your solid in. So your solid stuff comes in. Then you take a squirt bottle or something, or a pipette, and you slowly fill up the water until it gets just to that line. Okay. Now you know the grams of solute because you put them in first, and you know the total milliliters of solution because you've got now 50 milliliters of the solution, or 50.00 milliliters of solution, whatever it is. So that's how you often make solutions, and that's why this type of a measurement is really useful, because you can easily measure the volume of the entire solution, and you know the mass because you know how much you put in the first place. All right. So if you have, let's say, a 5 grams of KCl in 250 milliliter solution, you can say 5 grams of KCl divided by 250 milliliters of solution times 100% is going to be a 2% solution, mass by volume. So all of these measures, these three that we've dealt with, are going to give different numbers, almost always. So it's really important what type of percent you're talking about. The mass percent, we don't know the total mass of solution in this example, but the mass percent is almost certainly different from the volume percent, or from the mass volume percent. So we have to know which type of percent we're talking about, or we're going to get the wrong thing. Okay, so that said, let's take a quick break, like 10 minutes, grab some more candy, and then we'll come back and pull out your labs, and we will go through some of those calculations, and we'll have to post some data to Blackboard so that everybody can see our numbers. Oh, okay, yeah, thanks. Are you reading skills when you wrote this?
Why are you making me pay more chocolate?
I think it does.
Oh, this one here. I gave you this. Yeah, I told you. No, you want it? So again, I don't want it.
Sure, I'm sure that worked in the University of New York.
Hmm?
Hear about a chemistry lab that exploded?
No.
It was a huge freak accident at like Fordham University a week ago.
Oh, just a week ago? No, I haven't heard about that one.
I think it was like, wasn't this week, had to have been. 'Cause I heard about it on Monday. And it was over the weekend, so like on Friday or Saturday. in New York City. And they had to completely close down like the whole science lab and the whole science department to investigate. I had to think of this.
Fordham in New York?
I think it's one. But what is it? NYU?
University of Rochester.
I was there. All I could think of is, so did they get out of the class and they have like a pass for the rest of the semester because you have stupid friggin' students? And I think of this, I could put a couple people in this class to do something like that. Why can't it happen here? Your excuse for not. I'm like, it's not that. It sucks.
Yeah, I'm doing some lab work. Graduate students are doing lab work. And they didn't do their waste properly. Mixed.
Probably.
Yeah, that's what it says. They mixed waste that wasn't supposed to have been mixed. That's why we have like separate containers for different kinds of chemicals. Because sometimes if you put things in the same container, they explode. That happened here, not like an explosion, but it happened here in my lab a couple of years ago. Somebody put the wrong thing in the wrong waste bucket, and it started like popping, and brown smoke started like coming out of it, and it was going. And I looked at
What
it.
do they mix?
Nitric acid and organic compounds.
Did you guys like have to pull like an alarm or something?
No, it was just in the hood. It was fine, but it was a good
Did you guys,
example
like,
to not
shut
do
it
that.
down?
Luckily, it wasn't a huge amount. If it had been like a significant amount, it could have definitely exploded.